So when we are solving systems of equations in algebra, there are three main techniques. We learned when we were first getting started in our math journey how to solve systems of algebraic equations using the method of substitution. We learned how to solve them using the method of elimination. And then, if you've taken linear algebra, you learned a third technique, a way to use matrices and vectors to solve algebraic equations. Now, we have studied how to solve systems of differential equations using method of substitution. There is an optional video posted if you want to see what method of elimination looks like in that context. But what I would like to explore with you over the next couple of days is how to use linear algebra techniques to solve systems of differential equations as well. Now, if you've already taken linear algebra, the next couple of days are probably going to be pretty relaxed for you because we're going to start with a very basic and very limited overview of some of the main skills that we are going to need from linear algebra in this section of the course. Today we are going to be reviewing matrix multiplication, and then tomorrow and the day after that, we will be reviewing how to find eigenvalues and eigenvectors of matrices. Now, to get started talking about matrix multiplication, I would like to familiarize you with the way in linear algebra that vectors are denoted. In physics, a two-dimensional vector is usually denoted using the standard basis vectors I hat and j hat. In calculus, by contrast, that same two-dimensional vector would be denoted using angle brackets, angle bracket 2, 3. But in linear algebra, this same vector is written vertically. The vector is surrounded by either large parentheses or large brackets, and the two entries of the vector, instead of being written side by side, are written vertically stacked, the x-coordinate on the top and the y-coordinate on the bottom. So the first thing that I'm going to do is I'm going to show you how to multiply a matrix and a vector. And then once we have had some practice with the basic calculations, we're going to explore what is happening when we multiply a matrix and a vector together. For example, in this exercise, we have the vector with 4, the x component, written on top, and 2, the y component, written on bottom. So recall that this would be equivalent to what we call in calculus angle brackets 4, 2, and that would be in turn equivalent to what in physics is called 4i hat plus 2j hat, just alternate notation. And this question is asking me to take that vector and multiply it by the matrix 3, 5, 1, minus 2. Now the result of this calculation is going to be another vector, another two-dimensional vector. So I need to figure out what is the x component of the answer and what is the y component of the answer. To figure out the x component of the result, to figure out the number that would go in the top part of the answer, I'm going to start by looking at the top row of my matrix. I'm going to take that top row and I'm going to multiply the first entry in the top row with the first entry in the vector. And I'm going to multiply the second entry in the row with the second entry in the vector. So 3 gets multiplied by 4, 5 gets multiplied by 2, and then I'm going to add those two numbers together. 3 times 4 being 12, 2 times 5 being 10, add those two numbers together, and you get the top entry in the answer of this calculation. Now, if I want to find the number in the bottom of this result, and I'm going to take the first entry and multiply it by the first entry in the vector, the second entry in the row multiplied by the second entry in the a vector. So 4 times 1, negative 2 times positive 2. Take those two values, add them together, and you get the y component, the second entry in the result. So after simplification, what is the result if I multiply the vector 4, 2 by the matrix 3, 5, 1, minus 2? My result is the vector 22 in the x component and 0 in the y component. Now let's do this one more time to make sure that we understand the method. Here, I would like to multiply the vector 1, comma, minus 1 by the following matrix. In the top row, negative 1, 2, and 3, 4 in the second row. Now the answer is going to be another vector with two entries. I just need to figure out what number goes in the top and what number goes on the bottom. Now to find the first entry, I'm essentially going to take a dot product. I'm going to take a dot product of the matrices first row with the vector in green that I'm multiplying. So the first entry gets multiplied by the first entry, the second entry by the second entry, and then I add the results together. So minus 1 times positive 1, result negative 1. 2 times minus 2, result negative 2. And that sum, negative 1 plus negative 2, would be the first entry in the answer. Similarly, for the second entry, I'll take the second row of the matrix, multiply entry number 1 by entry number 1, entry 2 by entry 2. Once I've done those two products, I add them together, giving me 3 times 1 plus 4 times minus 1. So after simplification, the answer to this question is the vector negative 3, comma, minus 1. Let's mix up the question a little bit. In this case, I know what my matrix A must be. My matrix is 2, 4, 2, 1. I would like to multiply that by a non-zero vector v, and I would like the result to be equal to 0, comma, 0. Now, in order to make this equation true, I would need, first of all, to be able to calculate the product of the first row in the matrix with this vector v and get 0 as the result. So 4 times v1 plus 2 times v2 would have to equal 0. At the same time, it would also have to be true that the product of the second row and the vector would have to equal 0 as well. So 2 times v1 plus 1 times v2 would have to equal this 0 down below. Now notice that actually these two equations are exactly the same. If you cut equation number 1 by half, then it becomes identical to equation number 2. So there's a bit of redundancy here. Because of the redundancy, really all I have to do is find some non-zero vector, some v1 and v2 that satisfy this equation in gold, and then I will have answered the question. Now I think the cheapest choice here, the simplest choice, would just be to fix v1 to be a really simple number, like just the number positive 1. And that would force v2 in this equation to be equal to minus 2. So the vector that this question's asking for, the vector v, one choice would be 1, comma, minus 2. It's not the only vector that would satisfy the requirements in this problem, For example, if I had chosen a different V1, if I had chosen V1 equals, for example, 3, then V2 would have had to be -6 to match. So 3 minus 6 would be another possible answer to this question. Now, what's interesting about the previous example, and what's going to come up pretty often for us as we're using this technique in our future calculations. When we were doing these calculations, we ended up with two equations that were redundant. One of them was just a scaled up version of the other. And that was a result of the fact that in the actual matrix, one of the rows was a scalar multiple of the other. Row number 1 was just 2 times row number 2. So functionally, because the second row in the matrix was a scalar multiple of the first, we really, in the end, just used one of the rows to answer this question. For example, we used 2 times V1 plus 1 times V2, that must equal 0 to answer this question. Now that we've talked a little bit about how we multiply vectors by matrices, let's talk a little bit about why we might multiply a vector by a matrix, by what effect that matrix has on that vector. Now, the effect of a matrix on a vector depends in part on the nature of the matrix. There are a couple of matrices, for example, who have the effect of changing a vector's length. For example, consider the matrix 2, 0, 0, 2. I want to study for a moment what will happen if I took this particular matrix A and used that to multiply vectors. So, for example, suppose that I took the matrix A, 2, 0, 0, 2, and I used it to multiply a random matrix, for example, 1, comma, minus 1. Let's see what the result is equal to, and let's see how the answer compares to the original. If I multiplied this vector and this matrix, then to find the top entry in the answer, I would have to do 2 times 1 plus 0 times minus 1, so all in total, 2. To find the bottom row of this vector, to find the second entry in the answer, then I would have to take the bottom row of the matrix and do 0 times 1 plus 2 times minus 1. Now notice something. Compared to the original vector 1, comma, minus 2, the answer is simply 2 times as large as what you had before. The effect of this matrix on this vector is to scale it by a factor of 2. This particular matrix, 2, 0, and 0, 2, will have the same effect on any vector that you give it. If I try multiplying, for example, a generic vector, v1, v2, by this particular matrix, then the result of this product will be 2 times v1 plus 0 times v2, 0 times v1, and 2 times v2. So basically, no matter what vector you start with, this matrix will have a consistent effect of causing the vector to become twice as long as it was before. Now, other matrices have other effects on vectors. For example, consider the following matrix: A equals 0, comma 1, negative 1, comma 0. Let's see, for example, what happens if we apply that matrix to the vector 1, 0. If I calculate this product, then the top entry would be 0 times 1 plus negative 1 times 0. So 0 plus 0 would give me 0 in the top entry. The bottom entry would be 1 times 1 plus 0 times 0. So 1 plus 0 would be 1 for the second entry. Now, to get a better idea, to get a further grasp on what this particular matrix is doing, let's go ahead, for example, and see what happens when we apply this matrix to a different vector. For example, let's see what happens when we apply this to the vector, let's say 0, 1. So 1, 0, who started out pointing to the right, ended up as a vector that was pointing up. Let's see what happens if we start with a vector that's pointing up. What will the result be equal to? If I calculate this product, then 0 times 0 plus negative 1 times 1 will give me negative 1 for the first entry. And then 1 times 0 plus 0 times 1 will give me 0 for the second entry. So the answer is now a vector that's pointing to the left. So what do you think? When I applied matrix A, this yellow vector, which pointed to the right, in the end pointed straight up. When I applied that same matrix to this vector that's pointing up, in the end, it pointed to the left. If you had to guess, if I fed it a vector that was pointing to the left, what would happen to the answer? What direction would it be pointing? Well, a consistent pattern that I'm noticing in the previous two answers is that the result is always a rotated version of the original vector. Take the original vector in yellow, rotate it counterclockwise by 90 degrees, and you get the answer. So based on that, I would predict that this yellow vector pointing to the left would be transformed into this blue vector pointing down after the matrix A was applied. So this matrix has the effect of taking vectors and rotating them through an angle of 90 degrees. As it turns out, in general, if you take A equals cosine of theta, sine of theta, negative sine theta, cosine of theta, that this matrix will have the effect of rotating vectors through an angle of theta degrees, whatever it might be in your particular problem. Let's go out to Desmos and see that effect in action. To prepare for that, let's take a quick moment to write down an expression for the result of multiplying a random vector by this particular matrix. Sine theta, negative sine theta, cosine theta. Let's multiply it by a random vector, maybe 1, 2. Let's write down an expression for the result and then plot it on Desmos to see what the answer looks like for various theta values. So the first row would be cosine times 1 plus sine times 2, negative. So cos minus 2 sine theta. And the answer for the bottom row would be sine times 1 plus cosine times 2. So that would be sine theta plus 2 cos theta. And that would be the y component. That would be the second entry and the answer. Let's go to Desmos and let's graph this and let's have a look at what's going on. Okay, here I am on Desmos looking at the graph of the vector 2 for the first entry and, 1, 2. And here in the brackets, I've written down the formula that we created for the result of the transformation: cosine minus 2 sine for the first entry, and sine plus 2 cosine for the second. The only modification I've made is that instead of using theta, I'm using the letter A for the angle. Now this slider down here controls the angle A, and as the angle A increases, we see that the image, the result of the transformation, this blue vector, get rotated through various angles. For example, as I increase the angle A, we can see that the result of the matrix multiplication is a rotated version of the original vector, and the degree of rotation, the amount of rotation, is controlled by the angle A, which is inside sine and cosine. So as you might be able to imagine, linear algebra and matrix multiplication are extremely useful tools in computer image processing. Matrix multiplication can be used to scale images, for example, to make them bigger, for example, twice as large as they were before, or to shrink them and make them smaller than they were before. Matrix multiplication can also be used to rotate or even to flip images. For example, here, this matrix could be used to rotate an image through 90 degrees. Most matrices, however, have different effects on different vectors. For example, if I consider this matrix, -1, 1, and 4, -1, we will see that the effect of this matrix will be different depending on the vector that we apply the matrix to. If, for example, I applied this matrix to the vector 1, 0, if I look at the result of that product, the top entry would be -1 times 1 plus 1 times 0, result -1. And the bottom entry would be 1 times 4 plus -1 times 0, result +4. And so this vector not only points in a vastly different direction, it's also much longer than it was before as a result of having this 4 in the y component. But if you feed this matrix a different vector, for example, if you applied it to the vector 1, 2, in this case, if I apply this matrix to this vector, the top entry is -1 times 1 and 1 times 2. So the result of that would be -1 plus 2, so +1. Then we have 4 times 1, -1 times 2, so that would be 4 minus 2, that would be 2. This particular vector is completely unchanged by application of the matrix. If I feed this matrix yet another vector, for example, if I did 1, -2, then -1 times 1 and 1 times -2 would give me a result of -3, I think. And 4 times 1 plus -1 times 2 gives me a result of 6. And compared to what I originally had, this vector is scaled by a factor of -3. That both the x component and the y component are -3 times what they were before. So for matrices like these, what we will be learning over the next couple of days is how to find these kind of special vectors for the matrix. These special vectors which are either unchanged when the matrix is multiplied, or which are scaled when the matrix is multiplied. These vectors have a special relationship to the matrix and have special uses in many problems, and so we give them a name. A vector that is scaled when multiplied by a matrix A is a so-called eigenvector of the matrix. For example, in the previous problem, with the matrix A equals -1, 1, 4, -1, the vector down here, 1, -2, would be considered an eigenvector. Because when we multiplied it by the matrix A, the only thing that happened was that the answer was a scaled version of the original. It turns out that the vector 1, +2 is also an eigenvector of this matrix. The vector was unchanged when the matrix was multiplied, so it was, in some sense, scaled by a factor of 1. Multiplying by 1 doesn't change anything. So if the vector was unchanged, it also counts as an eigenvector. Now, the amount by which an eigenvector is scaled is also an important number that we will be using in many problems. The amount by which an eigenvector is scaled is called the eigenvalue corresponding to that eigenvector. So, for example, in the previous exercise, when I applied the matrix to the vector 1, -1, the answer was a scaled version of the original, scaled specifically by -3 units. So in the new language, what I would say is that -3 is an eigenvalue of the matrix A corresponding to the eigenvector 1, -2. From the previous example, I could also say that the number 1 is an eigenvalue of the matrix because when I multiplied the vector 1, 2 by the matrix A, the answer was 1 times the original vector. Now in tomorrow's class and the day after, we will get some exercise finding the eigenvalues and eigenvectors of a matrix. And then in the 2 days after that, we will see how we can use eigenvalues and eigenvectors to help us to quickly solve systems of differential equations.